So welcome to my next webinar in my series on modern Java by example. Over the past several days, we've been talking about the folders program, which demonstrated the use of sequential and parallel streams, the RxJava framework, and the Reactor framework. Today, we're going to change up a little bit, and we're going to talk about a very interesting program, which is called EX1, for reasons you'll see in a minute, which are going to demonstrate a whole slew of advanced Reactor features, and we're going to use them to do various computationally intense processing operations. So let me first show you where we're going to be looking at the code, and then we're going to go ahead and dive right into the analysis. So let me start by sharing my screen, and you can find the code that we'll be talking about here in my GitHub repository under the Reactor folder in the EX1 directory. And so all the source code we're about to look at is here. This is actually a variant of another program we'll probably talk about tomorrow that does more or less the same set of things, except the example we'll look at tomorrow uses Java's completable-futures features instead of the Reactor features. And so it'll be really fun to compare and contrast the different ways of doing things. So this approach is fundamentally about asynchronous processing using Project Reactor operations. So let's now go ahead and switch over to my IntelliJ, and we'll go ahead and get started. So you can see if you come in here, there's a program EX1 for example 1 here, and over time I'll add lots more Project Reactor examples, I'm sure. And so what we're going to do is we're going to use this test driver program to illustrate various ways of reducing and or multiplying big fractions asynchronously. And we're going to do this in order to demonstrate a wide range of features in Project Reactor, including flatMap, which we've looked at many times before, collectList, which we really haven't looked at a whole lot, zipWith, which is interesting, first, when, and onErrorResume. There's some other methods we'll take a look at along the way, like do on success and so on, that we've seen before. And we're also going to look at a very interesting method called then, which is pretty funny. So let's go ahead and jump into the example. We define a few finals up here just to make the code a little cleaner down below. As you'll see that this is a fraction multiplication program, big fraction multiplication. So we define a bunch of strings that will contain various fractions or numerators and denominators. You'll see how those things get used in just a second. We then go ahead and define ourselves a big reduced fraction, which has a very large numerator and a very large denominator. And we pass in the true flag, which means reduce this. So this will be a reduced fraction. We also define a final mono, which is given the value of the big reduced fraction. So the mono.justCall here, just is an eager operation with mono, unlike most other operations, which are lazy. So this will go ahead and emit the big reduced fraction, and it'll store it here in a mono. And we're going to use that to simplify some of the processing later. We also have another very interesting mono here. I call this S-void mono, or S-void M for S-void mono. And this is just an empty mono. And you might think to yourself, what the heck good is an empty mono? Well, you'll see what good an empty mono is later. Empty monos are a little bit persnickety in some cases, but they're very useful for the purposes that we're going to use our program for. Okay, so now let's go ahead and show the main function in the program. Now, if you've been watching a lot of my webinars, you'll know one of the things that we typically do is we end up putting these blocking statements at the end of a lot of our test methods. So we'll do, when we were doing RxJava, for example, we used blocking subscribe. When we were doing Project Reactor yesterday, we used the block method in a number of cases. And there's other things you can use to block as well. And that's really just there for testing purposes, because if we don't block, then these examples will end up returning very quickly and will fall off main unless we put some kind of a sleep statement. Well, that's all really annoying. So I wrote a little test driver program here that makes it easier for us to manage examples that don't block. And so I call this thing async tester. And we're going to look at async tester in a second. But before we do that, notice what I do with async tester is I take all the functions, all the methods I want to test asynchronously, and I register them with the async tester. So you can see I've got, I think 7 or 8 different methods. I think I have 7 these test methods here, like test fraction combine, test fraction multiplication callable, test fraction multiplications 1, and so on and so forth. And we go ahead and we register all of these things. And then what we're going to do is we're going to go ahead and run all the tests. And run tests is a very super clever mechanism that's going to go ahead and start all of those asynchronous computations. And we're going to go ahead and run them all. And some will run synchronously, some will run asynchronously, depending on how they're programmed. But irrespective of whether they run synchronously or asynchronously, they're all going to return an empty mono. And then we're going to use that empty mono to wait for everything to finish running. And then we're going to go ahead and finish the tests. So you'll see here when we run tests, as we'll look at in a second, it's going to go ahead and asynchronously kick everything off. And then we're going to have this thread block for everything to be done. This is a little bit kind of along the lines of our futures collector that we've talked about in previous sessions that had to do with the way in which we handled a lot of completable futures that had to finish. So this is kind of in the same vein. So let's go ahead and take a look at Async Tester. And this will also illustrate some cool features of the Reactor framework. So Async Tester is going to have a list of suppliers to mono voids. Okay, we'll see how that gets used in a second. So we have a new array list of these things. And then we have a method called register that takes a test, which is a supplier mono void, and it goes ahead and it adds it to the list. So when we do that add call over here, the register call that you saw back over here, all these register calls are basically just adding the suppliers to the list. So that's how we're going to store all the computations to execute. And then when run tests gets called, so after we've configured everything to have all the tests we want to run, we then go ahead and use a flux to convert the tests array list, or list in this case, into a flux of supplier monos. So we have a flux stream. We have a stream of supplier mono voids. And then for each of these things, we're going to call the flatMap operation on each one. So what that's going to do is the flatMap operation will go out there and it'll call the get method on each of these registered tests. And that's going to turn around and start the test running. So for example, if we had registered test fraction multiplications 1, or test fraction exceptions 1, or test fraction multiplication 2, all those tests get called when their run method gets called because they're registered as suppliers. And then what we do is we collect everything up into a list. So we have a list of mono, we have a collect list will return a list of voids because each of these things returns basically void. And so we'll have a mono to a list of voids. And this will be triggered when everything is done running. Now we could also use another technique here called next, which basically does essentially the same thing. So we have next returns a mono to a void, collect list returns a mono to a list of voids. It turns out that a list of voids might as well be a void. There's really nothing for it to do. And if you try to like count the number of elements in a list of voids, it'll end up being 0. So in any case, we're just basically waiting for all those asynchronous operations to finish. When they're all done, we go ahead and essentially get the next element. And then at that point, we return a mono, which will be the size of the number of elements that ran. So that's what comes back here to the main program. And then we can go ahead and block waiting for that. So now what we're doing here is we're basically having all these tests run asynchronously. None of them have to block. And then we're having this one point where we wait for everything to finish. So I just wanted to show that idea first. And then as we look at the various tests, I think it'll be a lot more clear how we're using this. Okay, so let's go ahead and take a look at a really simple example. This is nothing fancy. This is just using Project Reactor mechanisms to perform a big fraction reduction, and it has a pipeline of operations, and everything here runs in the calling thread. So there's nothing asynchronous about this at all. This is just a baseline example. So we go ahead and, the other thing we're going to do is we're going to use a clever string builder or string buffer to store the information so we can have all the output looking really cool. This is probably a good time to show you what the output looks like. So if I run the program, as you can see here, it goes ahead and it starts running all those operations, mostly asynchronously. And as they complete, it prints the results to a string buffer, and that string buffer is then displayed when the operation is finally done. And so you can see here, the final operation runs for a while, and you'll see why when we take a look at this later. But basically what we've got here is testing the fraction reduction, and that produces some results. Testing fraction reduction async, that produces some results. Test fraction multiplication callable, that produces results. We've got a real cool example here that uses fraction exceptions. So we do some exception handling. That'll be fun to see that. And then we have a couple of really interesting and advanced techniques for doing multiplication basically asynchronously. And there's a whole bunch of different cool examples. So we'll take a look at those in just a second. But I wanted you to see the output. So the output always tells you what thread things are being run in when they're done. And you can see that sometimes they're called in the main thread, as with the case with the synchronous version. And most of the time, they're being called in a background thread. Anything that doesn't have the value 1 is being called in a background thread. And anything that has a 1 here is being called in the main thread. And you'll see the two examples where things are called in the main thread in a minute. Okay, so that's what the StringBuilder stuff is for. It's just to be able to have the results buffered in a way that we can print them when the operation is finally finished running asynchronously. So we make ourselves a big unreduced fraction, passing in this big integer and this big integer. So these are big numerators and denominators. And then we go ahead and make ourselves a callable called reduced fraction. And what reduced fraction is going to do is it's going to go ahead and reduce that big fraction as shown here. So we go ahead and we'll reduce this, and let's see. So that'll just go ahead and reduce it. And then you can see that we append the results here so we can come back and see them. And this returns a reduced fraction. So this is just a callable. And if you recall, the callable, it doesn't take any parameters, and it goes ahead and returns a result. So it returns the result of doing a reduced big fraction. Then down here, we're going to define ourselves a function called convert to mixed string, which takes a big fraction and converts it to a string. We first log this by appending it into the StringBuilder, and then we return the result as a mixed string. And then the final lambda function is a consumer. In this case, it's going to be something that will print the results. So remember, consumers don't have any output. And so whereas a supplier has output, but a consumer doesn't. And so in this particular case, we're just going to go ahead and display the string that we've been building up with the StringBuilder as a string. And that's how it gets displayed to the output, as we saw over here. Okay, so let's go back and take a look at what this method does. You can see what it does is it takes the reduced fraction as a parameter from callable. So we have mono from callable, creates a mono of a big fraction. And keep in mind, this is not running in the background. This is running in the calling thread. We then go ahead and convert that reduced fraction to a mixed string. And then if everything goes well, we go ahead and print the results. So very simple. This looks actually quite a bit like using Java CompletableFutures, where from callable would be something like supply async. Map would be something like, say, then apply. And on success is something like then accept. But it's really sort of more like then apply. And then the last thing we do here, notice how we return the results of this pipeline. The last thing we're going to do is we're going to return a .then. And a .then just produces an empty mono. And an empty mono really has no purpose other than to be used in the fashion we used it earlier to say when everything else is done, then this thing will finish too. So it's a way of allowing us to wait on its completion. So it's kind of like returning a completable future to a void and then joining on it later. So that's what then does. It returns an empty mono. All right, so that's pretty simple. Nothing too interesting there. And if you look at the output, you can see that it did it all in the calling thread, and it all ran synchronously, and it gave back a sensible result. So now let's go over here and take a look at a more interesting example. This is going to do the same sort of thing, except now we're going to do this asynchronously. So we're going to have the same unreduced fraction. We're going to have the same callable reduced fraction. We're going to have the same convert to mixed string. This is all the same as before. We have the same print result. Same. The only difference is rather than doing from callable off of flux or mono, what we're going to do in this case is we're going to use from callable concurrent. And if you recall, from callable concurrent is a little helper method that I defined that goes ahead and emits an item that's a callable and then converts it to run in this case, the common fork join pool. And we'll talk a little bit later about why we use the common fork join pool. There are other pools you can use in the framework, the Reactor framework. There's a parallels pool, for example. And but the parallels pool that you get by using the .parallel method on schedulers is not the common fork join pool. It's important to remember that. So I just happen to like to use the common fork join pool, but nothing stops you from using whatever pool you like. And chances are the performance will be roughly the same. Okay, so let us go now and zip back over here. So this particular pipeline does exactly the same thing the previous one did, except this time, as you can see when you look at the output, we're going to do it in a different thread. So this is running in a thread from the common fork join pool or whatever pool we happen to use here. And so what we've done is we've moved that computation off the main thread. So that in some sense is one of the meanings of the term asynchronous computation. So what will happen there is that when that call starts to run, if we go back over here, this call, the one that's inside of test fraction reduced async, that is going to return very quickly. It'll return a mono, and it'll return a mono that's empty, and that will trigger when all these other computations get done running in the background. So again, very much like CompletableFutures in regular Java or Java 8 and beyond, modern Java. Now let's go take a look at another example. This is just to show some diversity. This particular example is going to use a callable also. And here we're going to have the callable go ahead and multiply two big fractions together. So we go ahead and make ourselves a little lambda callable. And inside that lambda callable, we're going to go ahead and create two big fractions. And then we're going to multiply them together. And we're then going to do that by running this in the common fork join pool in the background. So this is going to return us a mono to a big fraction called mono. We call the variable mono. And that call will then be capable of running in the background. And what we're going to do here is when we say mono.block, now the call will start to run and the result will be generated. And we're going to block until we're finished. And then we go ahead and print the results by appending them to our StringBuilder. And you'll notice if you look at the results here that this also is called in the main thread of control. And that's because we're blocking. So unlike the previous call, which ran in a background thread off the main thread of control, this particular thread will run in the main thread of control. And I could have fixed this, of course, if I'd wanted to, just by having it return then and make this return, have this not sit around and block. I didn't have to block it, but I decided to show off explicit blocking. And just to make everything work consistently, I'm going to go ahead and return an S void M. And if you recall, the S void M is this predefined constant that's a final mono that's empty. It's a mono void that's empty. And so that'll just always trigger right away. Okay, so far so good. It's still not particularly profound and interesting yet, though. So we're about to talk about some much cooler methods that are part of the Reactor framework, and there's equivalents to these methods in RxJava as well that will showcase more interesting things. So this is a kind of a fun example. This example is called test fraction combine, and it's going to use zipWith. We'll see what zipWith is in a second. I think zipWith is a funny name. It's kind of like zipping things together, like a zipper would zip things together. So in this case, we're going to go ahead and create a new random number generator, and then we're going to go ahead and make a very large random big fraction. And if you go down here and look at make big fraction, it takes a random number generator and a Boolean flag to indicate if we want the fraction to be reduced or not. And we go ahead and create a big integer, which is a gigantic big integer, which has quite a number of bits in it randomly. And then we create a denominator, which is basically taking the numerator and dividing it by a random integer between the values of 1 through 10. So we're going to make a somewhat smaller denominator. And then we go ahead and make ourselves a big fraction with this gigantic numerator and this smaller denominator. And then we indicate whether we want this to be reduced or not. So if you look back over here, you'll see we want this thing to be reduced. And this is all going to take place in a common fork join pool thread. And then we're going to take the results of that big fraction, and we're going to go ahead and multiply it by a constant reduced big fraction. So this computation is going to take a while to run because that's a big fraction, and when you multiply big fractions, it takes a while. We're also going to create another mono to a big fraction. So this is M1. So M1 is a mono to a concurrently executing big fraction reduction and multiplication operation or operations. And then we're also going to go ahead and create M2, which is another mono to a big fraction. And it's going to do the same thing, except of course, it's going to do it with a different randomly generated reduced big fraction. So now we've got two big fractions that we want to be reducing and multiplying concurrently or asynchronously in threads in the common fork join pool. And again, you can use whatever pool you want to do this with. So now we've got two computations that are running concurrently. And what we're going to do is we're going to say return M1, which is a mono to this long-running computation. And I want to zipWith M2, which is another mono to a long-running computation. And so what zipWith does is it says, wait until both M1 and M2 are finished, and then go ahead and apply this operation. And the operation we're going to do is we're going to add the results of the reduction and multiplication of these two big fractions together to have a final combined big fraction. So these guys are going to go off and do their thing in the background. And then, of course, all this is taking place asynchronously, naturally. And then when zipWith is done, we go ahead and call doOnSuccess, or the Reactor framework calls doOnSuccess, which is this operation that will take in a consumer, and that consumer, as you can see, is going to go ahead and print the results out and display them. So it's going to stick that into the string buffer and then display the buffer. And then you can see what we do here is, because we want this thing to return a something that can be waited on by our async tester, we return an empty mono. But that will all be running asynchronously in the background. It'll probably run for a while before it actually completes. So zipWith is pretty cool. I think you'll agree that zipWith is an interesting method, and it's basically like then combine for Java CompletableFutures. So zipWith and then combine are very, very similar in terms of their semantics and their syntax, just a slightly different name. All right, next example, let's talk about handling exceptions. So we're going to define a helper tester method called testFractionExceptions1. And this is a really cool example. It shows off all kinds of interesting things. So the first thing we're going to do is we're going to end up creating a flux that emits two Boolean values, true and false. Okay? So you can see that flux just will generate a flux stream of Booleans. And then we're going to take each of those Booleans, true and false, and we're going to go ahead and flatMap them. And we're going to treat the flag, the Boolean, as being, should we throw an exception or not? So if throw exception is true, then we're going to go ahead and create a denominator that is 0, because of course, dividing anything by a 0 denominator will throw an exception. Otherwise, we create the denominator to be 1. So we're just basically toggling whether exceptions will be thrown or not. What we then do is we go ahead and run this computation in the background in the common fork join pool. And we're going to take the value 100 and we're going to try to create a numerator with the value 100 and the denominator that's either 0 or 1, depending on that flag. Obviously, if it's 1, the value of method of big fraction will work just fine. Conversely, if it's 0, the value of method of big fraction will throw an arithmetic exception, which is what we expect. So what do we do then? Well, what we're doing here is we are using the onErrorResume method, which goes ahead and handles exceptions. So this is a bit like the exceptionally method. If you're familiar with Java CompletableFutures, it's kind of like exceptionally. So what it does is it takes a throwable, and we go ahead and append the error message we got here into our string buffer this time, because these things could be running concurrently. So string buffer is synchronized, whereas StringBuilder is not. And then we go ahead and we just convert whatever the heck happened and say, just get back a 0, please. Now, obviously, we could throw another exception or something else, but in this case, we're going to keep going. So that's why it's called onErrorResume. So in this particular case, if an exception's thrown, we kind of log it, if you will, note it, and then we go ahead and just return 0, or a mono to 0. Otherwise, if everything went well, we do the doOnSuccess method, and that will go ahead and multiply the big fraction by this constant, and then print out the value as a mixed string. So what you can see we do here is this flatMap is going to end up creating a flux of big fractions, one of which will have had an exception, one of which will have not. And then we go ahead and we collect this flux stream into a mono list. So we're going to say collectList, and that goes ahead and returns a mono, one element, to a list of big fractions. And then when everything is done, we're going to use flatMap, and we're going to go ahead and print the results by the display call, which will basically print what was in the buffer. And then we return s void m. And this little trick here at the end using flatMap is just to make sure that we return a mono void from this particular function. So that's why we did that. Okay, so that is pretty daggone interesting and cool. And if you take a look at the run of this, you can see down here we have calling test fractions exception 1, and we end up with one result being 100 because we had 100 divided by 1. That's 100. And the other one was an attempt to divide by 0. So we get an exception divide by 0 error. Fraction denominator is 0, so that's what we printed out there. And then we get a result back of 0. So we kept things going. We didn't propagate the exception. We could have propagated the exception, but we basically caught the exception, kind of logged it, and then we resumed the execution. So that's what onErrorResume does. Okay, we've got a couple more methods to talk about, then we'll take some interesting questions, I'm sure. This is where we get really powerful features that do long-running computations. And this is the test fraction multiplications 1 method. And this shows the use of flatMap, collectList, and first. And this is a really fun example. So what we're going to do is we're going to make ourselves a little function, and it goes ahead and reduces a big fraction. So this function goes ahead and reduces and multiplies a big fraction asynchronously. So it's going to do this running in the background, and the way it's going to do it, of course, it's going to use the from callable concurrent method, which, as you know from watching the earlier discussions, goes ahead and kind of wraps the underlying schedule or subscribe on method using the common fork join pool scheduler. So it's going to do the big fraction reduce in a background thread to avoid clogging up the main thread. What we're then going to do, and this is pretty cool, once we're going to get back from this, of course, a mono, and then we're going to go ahead and flatMap that. And then when this mono that we are taking is the input parameter to flatMap, so basically, if you can think of this as like completion stage methods with completableFutures, when this computation up here finishes running, we've got a reduced fraction, and then we're going to kick off another concurrent operation, which will take the reduced fraction and multiply it by a constant. So this operation will run concurrently, and then when it's finished, we're going to run this operation concurrently. And they very well may operate in 2 different threads. So this use of flatMap here is a little bit like the then apply async or then compose async calls from Java CompletableFuture. I happen to like the CompletableFuture syntax a little better because it's more clear what the semantics are just at a glance, whereas you have to kind of know the idioms of the RxJava or Project Reactor frameworks to make sense of this code. But at any rate, these are all going to be done asynchronously. All right, so that's the computations we're going to have running asynchronously. And they're going to take a while to run because these are big honking fractions we're trying to do. It's computationally intensive. So here's some really fun stuff. We're going to write ourselves a little generator, and this is really cool. So I have a Reactor utils method called generate, and we're going to look at that in just a second. And you're going to see here in just a second what this is going to do. It's going to go ahead and make a big fraction, and it's going to make up to S max fractions big fractions. So we're going to make a bunch of these. Let's say S max fractions is 10. I think if you go and take a look up here, it's equal to 10. So we're going to generate 10 random, large, unreduced big fractions. And let's go take a look at the generate method and see how we do this with Project Reactor. So what we do here is we use the create method on a flux, and we're passed in a sync. And let's see, I'm not sure if we can get rid of the cast here. That may cause us some trouble. I think that's actually good. So this, you can see that this was working fine. And so what we do here is this sync is then used as a way to generate the results. So what we do is we have a long stream that goes from 1 to count and inclusive. So 1 to count, where count is 10 basically. And for each of the elements in that range, we're going to go ahead and generate the big fraction. So we're going to make a big fraction because supplier.get is going to be having that result from generating that. If you go back over here, back to EX1, you'll see that we're generating it with make big fraction. So this is then going to generate 10 of these big fractions. And when we're all done, we're going to go ahead and say this sync is complete. So we've finished emitting the number of elements that we wanted to emit. So that's how we're going to generate all these things. Strangely enough, there's no easy, succinct way of doing this with Project Reactor. You'll see when we look at the streams version of this, it's the Java streams version is actually more concise and easier to do. So I wrote a little helper method to make that work. So we're generating a bunch of random, large, unreduced big fractions. Then we're going to go ahead and flat map them. And what that's going to do is that's going to go ahead and have all these things running in the background in different threads in the common fork join pool. So all that reduction and multiplication of all these things that are generated will all be running asynchronously. And then we use collectList. And collectList is basically a variant of a collector. It's not quite like the Java streams collector. In fact, it's quite different if you look at the implementation. But the net effect of this is we're going to get back a mono, essentially, to the list of reduced and multiplied big fractions. And what we do then, and this is really fun, when everything is done running, we go ahead and take the list that came back. Now, keep in mind, at this point, we actually have a list. So if you take a look at the type here, you can see that it's list of big fractions. So we have a list of big fractions. We're no longer a mono or a flux or anything. And we're going to go ahead and sort and print that list. So let's take a look at sort and print list. And sort and print list is pretty cool. So what sort and print list does is it says, I don't really want to have to think hard about what's the best sorting algorithm for this list. So I'm going to do a quick sort and a heap sort, and I'm going to do them both concurrently. They'll both run in the background in different threads in the common fork join pool in this case. And whichever one finishes first, I'm going to take that answer. So this is an age-old trick of leveraging all the concurrent cores on modern processors for your benefit. And of course, we could use something other than quicksort. We could use merge sort or some other sort. It's not really important per se what sorting algorithm we use. It's just the fact that we're doing two of them in parallel. And then we're going to use another interesting method, which has a very bizarre name in RxJava, but in Project Reactor, they call it first. It used to be called first emitting, but now it's called first. in RxJava, it's called AMB for ambiguous. But here it's called first. And what that says is take a bunch of monos, and whichever one finishes first, take that result and use it. The other ones aren't canceled, they're ignored. So what happens here is whichever one of these sorting algorithms finishes first, we're going to take that one. We now have a sorted list, and we go ahead and we write each of the elements out into the sorted list. So here's what it looks like. Test fraction multiplications 1. It goes ahead and generates these absolutely gigantic big fractions. Look at these things. They are monstrous. And that's why it takes so long for the computation to run. And also why it helps to run all these things in parallel in the background. And when we're all done, we take the results, we do 2 sort algorithms on them, and then we pick whichever one finishes first, and we use that to print the results. You'll notice that that took a while to compute, but it actually took less time to compute than calling the test fraction combine test, which came first lexically, but took longer to run than test fraction multiplications 1. We're next going to take a look at test fraction multiplications 2, and that one was also a real fun example. I had a good time writing this one. So let's take a look at that one. So here is test fractions multiplications 2. This one is purely there just to show off some interesting things. This combines the Java Streams framework with the Project Reactor framework, and it has them both working together. And it's really kind of cool. It's kind of amazing that they work together, but they do work together. It's just not as fast as doing this with Project Reactor alone for reasons we'll talk about in a second. So what we're going to do here is we're going to go ahead and do the same from callable trick here for reduce and multiply fractions. And I guess to be fair, we probably should do the same computation as we do up here, running this guy in the background as well. That'll probably speed things up. I'll probably make that change here soon. So anyway, we're going to do some things concurrently. And then down here, take a look. Now we're going to use stream as opposed to the flux stuff. So Java Streams has a generate method. And unlike the kind of wacky thing that you have to do with Project Reactor or RxJava to start emitting things and saying next, 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 complete when you're done, this is going to just use the stream generate method. We're going to give it a lambda supplier, which is going to generate a bunch of big fractions that are large, random, and unreduced. And we're then going to limit it to this many. And then we're going to go ahead and use map. Now, this call to map is actually the Java Streams map. And this is a sequential stream, so it'll run sequentially. So this part won't be running in parallel. And then we do something really cool. Remember, this is Java Streams, so we can have a collect call. This is the Java Streams collect method. And we're going to collect into a MonoCollector. So mono or mono's collector is a little Java collector that I wrote just to have fun with yet another set of features of the Project Reactor framework. So the two mono method, I probably should call this two monos, but it's actually, I take it back, it's two mono. We get back one. We'll make a mono's collector. And here's what a mono's collector is. A mono's collector takes a Java sequential stream of monos, and it's going to internally keep a mutable result container that's a list of said monos to objects of type T. And it's going to return a mono to a list of T's. So it's very much like futures collector that we've looked at before, but this is for monos, not for futures, not for completable futures. So the supplier method returns an array list. That's what's going to be used to serve as the mutable result container. The accumulator method returns a by consumer that will be used to add a mono to the list of monos. The combiner method has a little lambda expression that will take two lists of monos and merge them. And then here's where things get really interesting. And it took me a while to figure this one out because it's very mysterious from reading the documentation on Project Reactor, which is a little Spartan in many ways. So what I do here is when I'm all done, I have my list of monos, and I go ahead and I say, hey, mono.when, here's a bunch of monos I want you to wait for. And monos.when will return a new mono that will complete when all the monos in the list of monos complete. So when all those other things are done running, then the mono returned from when completes. But what's weird, this is weird, is that the mono return from mono.when is a void mono. And there are very few things you can do on a void mono because it doesn't emit anything. So the one thing you can do with it, and this is just really hard to ferret out from the documentation, but I finally read enough Stack Overflow articles I could determine it. If you use the materialize method, this will signal when anything happens in a mono, even if it's a void mono. So whenever the mono materializes, which sounds sort of mystical, then this call will trigger. And then what we do is we use the flatMap call to take the list of monos, turn them into a flux, call the map operation on the stream of monos of type T in that list. And we use the block method reference here, mono block. This will actually never block because those things have already finished, and we know they finished because we would not have had something materialize had not all those monos we were waiting on complete. And then we collect all these things up into a list. So we end up with a list of type T because mono block returns an element of type T. This is very, very similar to the trick that's used for the futures collector that we've looked at in other lessons. And we'll see that again probably tomorrow when we talk about the completable future version of all this stuff. So this is some pretty crazy, weird, esoteric code, but it works. And it demonstrates this also somewhat wacky, esoteric use case of demonstrating that you can combine streams from Java with Project Reactor, and it all kind of hangs together somehow, which is pretty cool. And as before, we end up ultimately with a list. Notice this is a flat map, which is a streams flat map, not the mono flat map that we had used up here. That was this is the mono flat map here. This is the Java streams flat map there. And then we go ahead and do the same trick we did before of sorting and printing the list. Okay, so that's basically what I wanted to show you. I think it's a really cool example. This set of methods is really cool because it shows off all kinds of interesting features with Project Reactor. By and large, most of these features are also available in RxJava. They just look a little differently and they don't integrate quite so cleanly with some of the Java streams and modern Java functional programming features, but their functionality is there with slightly different names and slightly different syntax and slightly different behavior, but same basic idea. So the other thing that I think is cool is the use of this async tester to register all these calls. And you'll notice that none of them had to block at the end. That was the other thing I wanted to point out. None of these calls here blocked at the end. They all returned basically void monos that were either going to be used to wait for other things to finish, or they were just an indication that we're done if they were synchronous calls. So this is another cool little pattern. I think it's certainly useful for testing. It's also probably useful for kind of scatter, gather style programming where you want to start up a whole bunch of operations, let them do their thing, and then have one central thread that waits for them all to finish. So this approach would also be useful in that context as well. Okay, so that was a lot of stuff to talk about. So let us unshare the screen and we will go back here and take some questions. Let's see. Okay. So first question, is mono just similar to completable future completed? Yes and no. So mono just will go ahead and return you something, but what is returned is typically then fed into a pipeline of operations that will do other transformations to it. Completed, kind of the same thing, except you typically use the completable future. It's completable future completed is not really like mono just, because you can create yourself essentially a completable future that's empty, and then you can do some processing and you can basically join on that completable future, and it's not till it's completed that it goes ahead and allows joins to finish. The way I use just here is actually a bit more like the completed future mechanism in completable future, which we'll look at tomorrow. So it's not really quite the same. The mono empty trick, which is what I used there to create a void empty mono, that's more like completable future, completed future. And so I had something that could be used just as a way to do nothing but be waited upon when necessary. Let's see. The then API is similar to completable future void. So an empty mono, in some sense, a mono that's empty is similar to a completable future to void, in the sense that you just wait for it to finish, but you don't expect to get a result back. Transform deferred. So let's go ahead and take a look at the transform deferred question, because that's an interesting one. So the question is, what is transform deferred? And let's go ahead and pop back over here. Come on. There we go. Let's share our screen. We've talked about the concept of deferred, transform deferred earlier, but I'll be happy to go over it. Transform deferred is really the equivalent of the compose method in RxJava. So transform deferred is basically used to customize the operations in a pipeline of operations. So you can see here, for example, that we're saying, make me an item from a callable, make me a mono from a callable. And then transform deferred says, and run this operation in the common fork join pool. So that's what we're doing. We're wrapping those things up so that we don't have to write that code over and over again. So it says, run this in the common fork join pool. And you can see some other places that's very much like what custom would have, not custom, compose would have done in RxJava. So that's just showing how you can do the transform deferred. It basically can be used to have some operations applied to it and then get reapplied down the line. Let's see, let's stop sharing for a second. Okay. And let's see, next question. If we call block, then the entire pipeline runs in the caller thread, not the fork join thread. No, block only means whatever thread this thing happens to be running in, then make sure that when you reach that point in the pipeline, block at that point, no matter what thread we're in order for the thing to finish running. Let's see. If we use then and return it, clients can use callback methods instead of calling block. Yeah, if you look at all the examples I showed you there, we're using all those. I wouldn't call them callback methods. They're what completableFutures calls completion stage methods. Things like flatMap or do on success, collectList. Those are kind of completion stage methods, if you will. And so those are all letting everything run asynchronously until we're done. And then the last thing that happens is an empty mono, which triggers the async tester to return when all those things have finished running. Let's see. Yeah, so there's a question about futures collector. I showed an example. The monos collector is an example that's equivalent in many ways to futures collector. Let's see. So let's take a look at, all right, I'll come back to the thing about generate taking the sync. So the question about material, there are two things. There's a bunch of things that have to do with materialize. So it turns out if you have a list of voids, or like if you have a mono to a list of voids, then you can't do what you might want to do, which is basically check each of the elements in the void list. When anything is a void, it's just ignored. The one thing that is not ignored is the fact that it triggers, and that's what materialize is used for. So what we do there is it's just a way to get notified, even though we can't do anything to the values in this list of voids. We know when the last one is done, so it triggers the last call, which then causes the async tester to continue going. Let's see. In all the examples you've explained so far, everything was happening in a single JVM. Can you talk about how it works when the server is a TCP server and returns mono or flux? Well, pretty clearly, these mechanisms we're talking about are intended to run within the address space of one process. This is classic multi-core processing, which is exactly the same thing you get with Java streams, parallel streams, CompletableFutures, RxJava, and so on. They're meant to work within the address space of one process. So you can't be passing monos and fluxes across the network without lots of extra mechanism to kind of bundle them up and make factories to reconstitute what they're trying to do. Basically, they're intended for use in a single process in a multi-core system. So that's why it's concurrent and parallel as opposed to distributed computing. And then there was another example here, another question here about the generate that takes the sync. So let's go ahead and share the screen, and we will go and look at that. So here is what you're referring to. Let's see. This is the one that is here at the end of EX1. So if you go down and take a look at test fractions multiplications 1, you will see here that we have this generate method. That's my method, and we're going to pass in basically the supplier we want processed. So let's go ahead and take a look at generate. And you can see that the way this works is when we call flux create, then that is going to end up through the magic of, let's see. Let me add the explicit, whoops, that's not what I wanted. Let's add the explicit stuff here. Let's try to replace the lambda with an anonymous class. This will probably make it more clear. So remember, lambda expressions are just shorthands for the most part for anonymous classes. So you can see here, if this was the anonymous class we were defining, there would be a method called accept that's passed async. And the framework would be responsible, the framework, which is the Reactor framework, would be responsible for creating a flux sync and passing that to accept. And then you can see how sync is used in here to emit results that will ultimately flow back up the stream. Now, I didn't choose to do it that way, so let's go ahead and Control Z out of that. So what's happening here is that that's where the sync is coming from. It's coming from the flux framework, and it's passing that thing in. So that's how create works. It gives you a sync to kind of get the ball rolling. So hopefully that helped to explain it a little bit. That's one of the mysteries of programming with functional frameworks, is these variables appear to show up out of thin air. So we're almost done. There's another question here. What are the difficulties in implementing a server that returns mono? Well, it depends what you mean by server. If you mean server in the sense of client server, where the client is in one process, perhaps on one machine, and the server is in another process, perhaps on another machine, then as I just mentioned, you never return monos, naked monos from one to the other. Just like you never would return naked references to any Java object or C++ object for that matter, or C object for that matter, across a network. You have to do all kinds of other things that would be way beyond the scope of this discussion to talk about. So these mechanisms are not meant to be used in a distributed sense. These are not object references in the sense of, say, Corba. They're intended to be used within a process, and they're intended to be used on multi-core processors. And if you want to do inter-process communication, you can certainly do that using whatever mechanism you happen to like. You can use all kinds of remote procedure call or remote method invocation or data distribution mechanisms to send data back and forth. And then on the receiving side, you could have a little factory that converts whatever data came in into something that could then be processed and run through a flux stream or a set of monos or whatnot. But you never would be passing around naked references to any Java objects in a distributed system unless you're doing remote method invocation kinds of things, but that's not the point of these conversations. Okay, let's see. Yes, and so another observation here, which I'll just touch on. So the Reactor framework, Project Reactor, is done by a company called Pivotal, which is also instrumental in the Spring world, the Spring web services world. And there's something called WebFlux, and WebFlux is basically a Spring container that is integrated with the Reactor. And that's exactly right. So if you want to work with things once HTTP requests and responses come into your program, then you can use all these Project Reactor features we've been talking about natively in your app. You don't have to link in any other libraries. Of course, you could also use RxJava there, but you would have to bring those in on your class path and make sure that they were visible to you. So yes, there's a tight integration with that stuff. That, again, is beyond the scope of these tutorials, but for people who are building web services or microservices, you can, and you happen to use Spring as opposed to some other toolkit, then you can easily integrate all the stuff we've been talking about there. Great. So this is fantastic. Thanks again to everybody for coming and asking such good questions. What we're likely to do tomorrow is we will probably look at the completable-futures version of all this stuff. And it's kind of fun to compare and contrast that. So we'll probably show completable-futures, and then we'll do a sort of an apples-to-apples comparison. And I think, again, you'll probably notice that the completable-futures version is just a little cleaner because the methods are defined more explicitly to work in asynchronous ways. But I think you'll find that the Reactor stuff is a bit more generalizable because it also works for streams processing as well. Well, thanks again, you guys. I will look forward to seeing you tomorrow. Thank you, as always, for coming.